Tokamak.
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 Fusion scientists from all over the world have come together in ITER to build a tokamak, a fusion device that is based on the principle of magnetic confinement. The interior of a tokamak is shaped like a donut. Here, temperatures exceeding 150 million degrees Celsius force atoms of deuterium and tritium to fuse together, forming a hot plasma. The plasma must be kept in motion in the center of the chamber and away from the walls of the vessel. This is the job of the superconducting coils that surround the tokamak. With ITER, a new chapter in the book on fusion research will be opened, a book that scientists began to write some 80 years ago. Following the first fusion experiments in the 1930s, fusion laboratories were established in nearly every industrialized nation. By the mid-50s, various experimental fusion machines were operating in the Soviet Union, the United Kingdom, the United States, France, Germany, and Japan. Gradually, scientists' understanding of the fusion process was refined. A major breakthrough occurred in 1968 in the Soviet Union. Physicists Igor Tamm and Andrei Sakharov, inspired by an original idea from Oleg Lavrentiev, introduced a toroidal magnetic confinement device that they called a tokamak. The term tokamak is a transliteration of a Russian expression meaning toroidal chamber with magnetic coils. With their first tokamak device, the T1, Soviet researchers were able to achieve temperature levels and plasma confinement times, two of the main criteria to achieving fusion, that had never been reached. The tokamak remains the most promising technology for achieving fusion energy on a large scale.
Tokamak – это тороидальная камера с магнитным полем.
Тороидальная камера с магнитными катушками.
Tokamak.
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 Tokamak. Tokamak.
Tokamak.
We are able to launch lots of objects into the vicinity of Earth, what we call low Earth orbit. But the goal is points beyond. That transportation has not been fully developed.
Rocket propulsion today is remarkably inefficient. It works, but just barely.
And that is our game. That's where we play. What we're trying to build at Astra is a transformation engine that will redefine the way we travel in space, to make space transportation easy, affordable, fast, and economically rewarding. Space becomes then a place of business, a place of work. People don't necessarily just go to explore.
It's a slow, expensive, cumbersome proposition to explore space with the technology we have today.
And so we have to change that. Every ounce of fuel has to count for more. And that means the exhaust temperature has to be very high. The exhaust of a rocket is a few thousand degrees. We want it to be like the sun, 1,000,000 degrees. Or 2 million. No chemical reaction can do that. So we don't do chemistry. We use electricity. We go from gas to plasma.
Pulse.
There's something exotic about working with plasma, working with something that is millions of degrees.
The limit is that if you make it too hot, the rocket will melt. We choose not to be limited by metals or materials. Our pipe through which this exhaust goes is really a magnetic pipe, an invisible force. We have eliminated the most fundamental limitation in rocket propulsion, which is how hot you can make the exhaust.
We inject a propellant a neutral gas into an ionization chamber. We launch radio waves at it. Those radio waves convert that gas into a cold plasma. This plasma then proceeds into the booster section, the ion cyclotron resonance.
The next step would be to put electrical energy in to superheat the gas in a plasma state and accelerate it to the velocities needed for space travel.
Ultimately, our rocket can go further and faster than any other rocket that exists today.
And the rocket might be, similar size to what you would have for the chemical rocket, but now the propellant that you need is only this much.
The more cargo that you can carry for a given amount of ship, the more efficient your exploration program is going to be.
Space transportation will be part of our daily lives, and it has to be safe and affordable, and that's the next horizon.
VASIMR is one of those possibilities that will allow us to fundamentally transform space travel.
Most fuel-efficient, cost-effective way, which is a big business opportunity. The VASIMR engine can be the diesel engine of space.
And that is the promise of the technology, to make the ability to stay operating in space cheaper and much more sustainable than it is today.
VASIMR is one of the most interesting space propulsion concepts that I have ever seen.
Ad Astra and Franklin Chang Diaz and his team is making history. The VASIMR engine and the plans for its development are revolutionary.
I feel like I'm at the first step of Star Trek, creating the warp drive that's going to take people in future generations to great distances.
VASIMR will be a game changer. Space is very, very large, so we have a lot of work ahead of us, but really is nothing but ensuring our survival. That's what we're doing it.
"50 years ago, when people were super excited about nuclear power, we tried to put it on everything, including airplanes. There were some big operational issues. It wasn't safe. Fusion is a much safer option, a next generation of airplanes that doesn't rely on fuel and can just stay aloft, unlimited range, unlimited endurance. That's what nuclear fusion can do for an airplane. So nuclear fusion is the process by which the sun works. If you take a gas and you heat it up, eventually it separates into its ions and electrons. When the ions get hot enough, they can overcome their mutual repulsion and collide, fuse into one piece. When they do that, they release a lot of energy, 1,000,000 times more powerful than a chemical reaction, for example. What we're trying to do is control that reaction here on Earth. We put it in a magnetic bottle that can contain the high temperatures. You need hundreds of millions of degrees. We can release in a controlled fashion that energy. We think we have a very robust strategy going forward that has potential for success. What this concept does is it's a high beta concept, which means we use a high fraction of the magnetic field pressure. We use all of its potential. And that means we can make our devices 10 times smaller. So instead of something the size of a building, we have something the size of a large truck. The small is the reason we can do this quickly. If something's small, you can build up momentum, you can develop it fast. It doesn't take 5 years to design it, it takes 3 months. We can design it, build it, test it in under a year. We can do several of these cycles, and we think we can get to a prototype in 5 years. Every time you do plasma physics, you learn something new. And that's why this is a high-risk, high-payoff endeavor. That's what we're doing here, is testing that concept out to see if it really holds the promise that it appears to. And as a defense company, our increasing mission is to enhance global security, and this is how we do that in the energy realm. The world already does 40 gigawatts of gas turbines a year. The gas line going into that gas turbine, we're going to replace that with a heat exchanger coming off our fusion reactor. We basically use the gas turbine infrastructure completely. We partner with one of those companies, and we ship fusion-powered turbine plants around the world, and we expand that technology. Gas turbines are a huge improvement over other technologies in terms of climate change, but they're only a 50% improvement. We take it all the way. So no emissions, safe operation, proliferation-free. That means we can ship it to the whole world with a good conscience. Now, the old promise of atoms for peace was a noble one, but ultimately flawed because the technology wasn't right for it. We can achieve that grand vision and bring clean power to the world. The true atomic age can start. 10 years, we have great military vehicles. 20 years, we have clean power for the world. This isn't online by 2100. This is online by the time I can't even retire after we finish this. I still have to find another job after this is done.